I'd just like to introduce myself. So I'm Alex Bardell. I'm the chair of Green IT at BCS. I come from a technology background, so run left university, went to work for IBM for 20 odd years as a kind of technology person. So I've kind of worked through many facets. And then probably about 10 years ago, I decided to set out my own. I had a real interest with technology and sustainability. So I've kind of made that one of my areas, and I kind of work with companies to help them build out things like technology solutions for sustainability reporting, but also building end-to-end systems. I got kind of a bit of imposter syndrome because I came here and I thought, right, okay, I've got my giant slide deck of 300 slides. Let me have a look and see what I've got relating to mathematics. And I didn't find anything, which I thought was strange because a lot of people I work with are all from mathematical backgrounds. A lot of developers studied maths, done a lot of work in the insurance industry, and the actuaries and the risk calculation models are all based on mathematics. So somehow sort of mathematics and computer science seems to have fused together. So that it's just a given that it's maths form the basis of a lot of what we do. But what I'm sort of trying to find out is, what is the relationship between the two? So I kind of ask some of these questions is, where is the overlapping? Now, clearly, algorithms, so AI is an algorithmic-based thing. It uses vector databases, which have hundreds of thousands of different claims, which are actually used to then define the data. So this is a sort of response I got back, which said, these are things that obviously probability statistics, so data analytics, very big within the world of computing. Work with organizations like the Office of National Statistics, they're basically just analyzing data. So anything kind of data related, system designing, machine learning, all the things we do, they're of a kind of mathematics background, but somewhere along the lines, we sort of lost that pure relationship. So the mathematicians then become sort of more computer scientists or software developers. And clearly, if you look at an AI algorithm, that is clearly a mathematical model. But it's kind of like the people aren't really saying, actually, yes, I am a mathematician, but I'm a kind of more kind of computer scientist. So I kind of started thinking a little bit about, where does maths, energy, and computer science come together? So obviously, mathematical models, they're how you simulate complex energy systems, and it kind of forms the basis of it with a load of compute underneath. Software then translates these models into executable programs. The software then runs on data centers. These data centers are full of computers. These computers connect into the grid, and they consume energy, quite a lot of energy. So there is that kind of relationship. And one of the challenges that seems to have happened is that when I first started in tech, we owned a data center. The data center was in the basement. So when you went down there at the end of the year, the site facilities person would come and say, "Oi, that's your electricity bill. You've used all of this electricity." And you kind of knew that, but then things started transitioning into the cloud. And then you have cloud solutions, and that relationship between the data center and the compute and the work you're doing became one step. And now AI, you're now a second step because your prompt is talking to an LLM, which is then talking to a cloud or a GPU in a data center. And so it becomes difficult to understand the relationship between energy consumption and the mathematical models and the work you're doing is. And so if we are going to get to the climate change net zero, and if you kind of focus on what UK government is saying today, this is Ed Miliband, his perspective is we need to have a decarbonised grid. And what decarbonised grid means is we need a grid where we're not using any fossil fuels. And the challenge for maths and compute in this is, on one side, we're helping. So obviously, we're able to answer difficult questions. And I'm sure when I saw the previous slide deck and you're looking at the modeling, and I look at that and say, oh, I recognize that because that looks similar to the kind of outputs that a lot of compute is delivering. It does it at a cost, and the cost is energy. And in what is an increasingly competitive environment, that energy then becomes something that everyone's competing for. So if you're decarbonising transport, electric vehicles, that's electricity. If you're decarbonising buildings, so you're going from gas heating to heat pumps, that's electricity. So we're finding ourselves in this position where it's kind of like a perfect storm that everyone is transitioning to electricity. And at the same time, we already had a bit of a problem with data centers and compute, but now you've then put the AI question in there, and suddenly we find ourselves in this scenario where everyone is competing for this electricity, and it's getting to the point where, if we're going to get to where we want to get to, some things need to kind of change. And let's think about some of the models. So, mathematical models are coded into simulation software. Software provides us user interface, but also allows testing and redefining of energy models. So they're kind of keenly related. I think we're going to be dependent on mathematical models to help us do stuff. But we need to work out how to balance that with the energy consumption. So again, maths is important for actually doing energy generation itself. So it simulates outputs, optimizes models, and makes key data-driven decisions. And I'm going to talk a little bit at the end about the Met Office and how the Met Office is using maths, and it's using its weather predicting software to help us understand a bit better about what's actually happening in the weather, and how that weather then helps us generate energy. But I guess I could talk a little bit about what is the data center. So data centers are these huge buildings. You kind of maybe see them, you're going along and you just see this massive warehouse with no windows, no cars, no people, loads of security cameras and a big fence. And particularly with mathematical calculations, this is where we do a lot of work in things like the HPC computing world. So HPCs are these big, huge computer farms. They have high-speed switches underneath. And generally what happens is you have a load of data, you put it into your mathematical model, it generates a huge amount of data, which you then look at with your analytics tool, and it comes out with an answer, which in the case of actuaries and insurance is yes to insure, no to insure. But the process that you go through to get there involves a huge amount of compute, but it also involves a lot of calculations. And so typically, the insurance industry uses things like Monte Carlo scenario calculations to understand what the risk positions are. And increasingly, now we're looking at climate change. The UK government and many governments realise this. And I'm going to talk a little bit about upcoming legislation that calculating risk and climate risk is important, because we're already seeing climate events, and this is affecting how businesses make decisions. And then that will then come back to the fact we probably need people who can understand this and have an understanding of mathematical models to help define what these scenarios are and help calculate the risk positions for companies, and to understand whether what they're doing is beneficial for our climate change targets, i.e. is what they're doing going to help us achieve net zero, or is it not beneficial, therefore what's the cost associated with it? And finally, are we going to put ourselves in a position where this company is at risk because of rising sea levels, extreme weather conditions, and therefore any investor needs to understand and calculate that risk associated with that company. And this then becomes a key part of sort of financial reporting, which is sustainability reporting as well. And one thing I guess to point out is that some of these big data centers have a huge energy consumption. Mm-hmm. So the main big hyperscalers, which we call them, so these are providing services to multiple clients, or some of the giant GPU data centers for AI, they're consuming as much energy as a town. And it's huge. And I guess when we talk about data centers, I want to just say, what is a data center? So typically a data center is made up of racks of servers, high-speed network switching. We generally have on the high availability ones, power coming in from two places in the grid, and that's quite a lot of power. And the reason why you need two power supplies from a separate ring in the grid is if one goes down and carries on running. There's backup generators as well, which again generate either they're battery powered, so the battery packs are here to ensure that if the power goes off, you can switch to generators and emergency backup solutions. And then there's cooling. There's a lot of cooling. These things get really hot. Historically, we would have a kind of refrigerating air conditioning cooling system, but because it wasn't deemed to be that sustainable, it's decided we would move to water cooling. And now we've got millions and millions of litres of water being consumed in data centres. So much so that some of the things actually stopping us building more data centers is that the local water authorities feel they can't provide water needed. So maybe it's time to think slightly differently about how we deliver this. So where do the data centers reside? So weirdly, and I don't know why, but I think it's historically, because this is where the finance stuff was, and this is where most of the kind of technology-based requirements in the UK. So nearly all of our data centers are kind of in and around the Thames Valley, and a few spluttered around here. And obviously in Ireland, that's predominantly AWS. But the problem is Ireland's run out of power as well now. So AWS want to expand their capability in Ireland, and they're struggling to do it. The recent announcement, and we've got investment now in AI coming in. That was last week. The US government said they were going to invest billions in AI, but that requires data centers, and the predicted data centers will be consuming around about 6 gigawatts of power, which is the equivalent of 2 Hinkley Point reactors. They're 3.2 for the 55 new generators. And guess what? They want to put all the AI data centers in the Thames Valley, where the rest of them are. And obviously, we don't have the power and the grid to connect that. The UK is a bit behind in terms of getting its grid in place. So one of the reasons why wind turbine farms are not being built right now is because there's no grid connectors, so you can't generate any revenue from it. And at the same time, you've got electric vehicles and heat pumps all competing for electricity. So what could we do? Well, there are several options that people are considering, particularly for the AI data centers. So back in 2018, Microsoft created this, which was their data center in a tube, and they loaded it full of servers and dropped it into the waters off Orkney, I think. Left it there for 2.5 years, pulled it up again, cleared all the barnacles off, and had a look, and it basically functions as a data center. And obviously, if it's sitting in the sea, don't need to spend any money on cooling. And then, as is always the case, we didn't hear anything until a couple of years ago. The Chinese built exactly the same thing as a functioning data center, and they plonked that into the sea, and that's effectively running as a data center. But one of the advantages of doing this is, as we can see here, all of our connection points for wind farms are all on the coast. So we could probably think about installing our 45 AI data centers in coastal regions where we have the power supply, or in the areas we have the solar supply, and then that would allow us to actually have the power available. The only caveat, and I have my favorite website, I think is going to work. Come on. Let's see if this works. Okay, I see what's happening. Well, I need to share something else. How does this work? What should have done was gone to share. All right, stop share. I know, disaster, right, share. Let's go back again. Yeah. This, one of my favorite websites, is where UK energy is coming from. Now, yesterday flowing, that was about 50%. Today, we haven't got any wind, so suddenly gas has gone up to 23%. And sorry, 23% is actually coming on the imports. And gas, so we've had to suddenly power up all of our gas power stations because the wind stopped blowing. So obviously, the challenge that needs to be overcome is how to deal with that scenario. So if we build all of our AI data centers out on the coast and we plonk them in the sea, when the wind doesn't blow, it doesn't happen that often, we've suddenly seen that renewables, specifically wind, has dropped from nearly 40% down to 16%. So that's a huge drop. And the other thing we've got to be slightly worried about is we're consistently importing electricity from France, predominantly France and the Netherlands. So the UK is becoming increasingly dependent on third parties for their power. So there's a big ask, which is how are we going to build all of this capability to support the ongoing development of AI data centers? And you can look at this thing and it's great, and you could just keep watching and seeing how it shifts. But what it does really show us is that
plenty of solar today.
there's plenty of solar, sun shining, which is always good, but it's not consistent. So one of the things we need to address, particularly on something as power hungry as an AI data center, is how to deal with that. Right, there we go. So one of the other challenges, and this has really been seen in the USA more than here, is that in the USA have big initiatives to build out data centers in Virginia and Texas. And what happened was that because you suddenly had a huge hyperscale data center here, all the people living there suddenly realized that their energy bill just went through the roof. So there's some massive increase in demand for energy. And in some regions, they were seeing up to 25% increase in their electricity bills because these hyperscalers were just taking all of the energy. And the other challenge is they were just consuming all of the water as well. And maybe putting a data center in West Virginia or Texas isn't the best idea. So we like to put them up in Iceland because they've got geothermal energy, and then we just run a network link between there and the Nordics. So lots of data centers being built up in Sweden and Norway, or built under the ground. But if we're looking at some of the initiatives, they want to build a load of data centers in Abu Dhabi, which to me is not the best place because it's too hot, and you then have to deal with the problem with heat. But some of the challenges is that they're suffering infrastructure strains because it's a huge thing. And ChatGPT said they wanted to invest $1 trillion in data centers to meet the AI demand. Well, clearly there isn't the resources to actually service those data centers. And so the challenge, I guess, and the ask is, as a mathematician sitting there writing your models, run them through the computer systems that run in the data centers that call the power, are there ways you can write your models that don't use as much power? And there are some ways to kind of get that information back again. It's not ideal, but one of the things you can start thinking about is, how are my models consuming energy? And this is where we go on to these guys, and this is called the Green Software Foundation. And what these guys have done is built this ISO standard to help people think about writing code that's more energy efficient. And they've got this thing called the SCI, which is the carbon intensity rate for the code, and it focuses really on how you write the software, what libraries you're loading into the software, how you look at data. And data is an interesting one because depending on who you kind of listen to, between 25 and 50% of data is just what we call orphaned. It doesn't have, like, it had a structured source. I mean, a good example is I take a photo and I WhatsApp it to you, you then WhatsApp it to here, and suddenly this photo has now orphanized itself, and then it just sits there forever. And nobody ever comes along and says, oh, I'm going to delete all this orphaned data. So we've got disks sitting in data centers with networks consuming power for data which has multiple copies and really has no structure or home. It's just orphaned, but nobody wants to delete it because they don't know what to do with it. And it's even more complex with the AI models, that nobody wants to delete the data because they want to use any data they can find to train the models. And therefore we just have this problem where we could get rid of this data, but nobody does. And it's just this black hole sitting in the world of compute where we can't bear to delete and remove data, and it just consumes resources and brings nothing back again. So one of the things here that the Green Software Foundation and their ISO standard is looking at understanding where some of these wins are and how to write software and how to manage your data and where to put your environment. So if you want to build a technology solution in, say, Sweden or Norway, it's hydroelectric, so the carbon intensity of energy is very low. But if you build it in, say, Poland, where they're running lots of coal power stations, then the carbon intensity of your compute is much higher. But when you're sitting there writing a model, you don't maybe necessarily have the information to make that decision. And therefore, one of the things that we try and need to promote is the ability to understand what the actual energy footprint of the work you're doing might be. And this then rolls on to the other challenge. How do you know if your software is sustainable? The answer is you don't really, because if you go to a cloud provider like AWS or Microsoft Azure or Google Cloud and you say, I want to know what the carbon footprint of my resource, my servers, my data, my network is, they'll do that. But the problem is they all calculate it in slightly different ways. And if you write software in a specific way and put it onto a performance test harness and run that harness, and then you say, okay, and then put it onto a different performance test harness, they've always been geared to look at performance in terms of how much CPU or data they use, because that's what the cost is. Where it's quite difficult is there's no single standard to say, okay, I'm testing my software against a set of sustainability standards to understand that I've written good, sustainable software. So you can get cloud infrastructure information, but it's not all the same. And so without the development of a framework and a single standard and the framework that's adopted by everyone when they're writing software, it's going to be a bit challenging to understand. Yeah, I can share the slides. It'll be a bit difficult to understand how sustainable your software is. And it gets even more complicated when you look at how software is written. So you maybe have a digital app which calls multiple other applications and processes from across the world and brings it all together as one. So how do you measure the footprint of this component or that component? And this is where it gets a little challenging, and this is where maybe carbon reporting legislation that's coming along might actually help. I'm going to skip this one because it will take far too long to describe. But the thing I would just say at a very high level is people are looking at LLMs now. So everyone says ChatGPT, but it didn't always start off like this. With AI, it started off with simple models, and we have this concept of the elephant. Like the LLM is the elephant; it can do everything, but it's huge. And we've got the concept of mouse, which is the small language model, and the small language model can be trained on a large language model, but it only answers one specific question. And I guess if you're interested in what new car to buy, you don't need to know about a ragu recipe. And the problem with the LLM is you get everything. But the small language model can be more focused and deliver just a specific subset of the things you want to know. And it can actually be trained to a level where it can probably better answer your small set of questions than the large language models can. But the challenge is that right now, a lot of focus is on the LLMs. And there's another concept called model pruning. So when you actually analyze a lot of LLMs, 80% of them, that model is not being used, and neural networks don't do anything. So just as you come to prune your tree at the end of the year, you need to kind of prune out some of those neural networks that don't do anything. And then that makes your model a bit more light, a bit more efficient. And I guess the final thing is that we've developed AI to run on GPUs. The GPUs are what we have. Now, a bit unfair because people who build GPUs for AI are focusing on optimizing them for artificial intelligence. But there's a lot of research now says with different kind of technology architecture that we can develop. And that architecture is being designed from the bottom up just to deliver AI-capable calculations, just as Google's data centers are full of computers that are designed for Google. Maybe we need to focus a bit more on designing an architecture and a technology that actually can deliver what AI wants. So the next part, how much more time do I have? We're doing good.
We've got flexibility.
Okay. So one of the things that's really kind of more prevalent now in commercial world is this concept of sustainability reporting. So companies are being asked to report their sustainability credentials. And it's been around for a while, so it started in the 90s. It's kind of aligns to the UN climate goals. And so after Paris 2015, companies started doing greenhouse gas emissions with this concept of scope 1, direct emissions, scope 2, indirect emissions, scope 3, all of the emissions of your supply chain, upstream, downstream. And then from a more commercial perspective, we then started developing this concept of the ESG reporting. It's environmental, social, and governance. And then that became aligned to finance. So if a company wanted to access finance, specifically European Union finance, government finance, but also through financial organizations like BlackRock would be selling funds and financial tools and financial products to people based on their ESG rating, whether it's sustainable. And this was based on an understanding that younger investors who wanted to invest their money in pensions and things had a requirement for a higher level of sustainability to be associated with it. But then ESG reporting sort of ran into this kind of political battle between the right and the left in America, and they particularly disliked the S bit of ESG reporting. But then in the COP26 in Glasgow, there was an idea that actually sustainability reporting needs to align more closely to financial reporting. So the ISSB, which is the International Sustainability Standards Board, was set up. And then they went to go and ask the IFRS, who do financial reporting, to see whether they could build a model that would then allow us to do financial reporting for sustainability. So it's ESG, but just the next generation. And in 2025, so the end of 2025, start of 2026, the UK is going to implement the SRS, which is a sustainability reporting standard. And the objective of this is to now move to a more financial-based reporting where companies need to report, as I said earlier, their risk. So what is the risk they face from climate change, their benefits, and it's something that then becomes more aligned to financial reporting. So one of the challenges that the UK faces is there's no money. So the UK government's got no money, so it can't pay for any of these sustainability initiatives that it wants. So, but it wants them to happen. So the way they're going to try and approach it is that they want industry to pay for it, so that when you decarbonise the grid, they want industry to pay. When companies achieve their net zero targets, they want companies to pay. And this is one of the tools, the kind of triggers and the pokers that they can get people to do it, which is you need to do your sustainability reporting, and that will then provide a level of, I guess, maturity, which the financial markets can then invest in based on how mature you are, how good your kind of net zero targeting is, how sustainable you are as a company, or how sustainable you've become. And therefore, this requires a lot of data. So you need to go, particularly with Scope 3, you need to be able to collect data from your entire supply chain, pull that again to a single point view, and then run analytics either through an AI, something like an agentic AI prompt, or using mathematical modeling to then extract that data and say, this is where we are against the set of criteria that are published in the standard, and therefore this is what we need to do to be more sustainable. And that actually requires quite a lot of data analytics. And this is why it's proving to be a bit of a headache for companies now, because they find this quite difficult. So if we're thinking it from a computer perspective and a mathematical perspective, are there ways that we can simplify companies' ability to collect this data and to do their reporting? And so one of the obvious ones is this concept of agentic AI. And what agentic AI is actually looks at data, develops a process, creates the outputs, in this case, reporting. And as the reporting standards develop, agentic AI will be able to understand what changes are coming, go back, update the business process, view the data sources, and develop the reporting standard as part of an agentic AI model as it goes on. So just my final slides is, what's AI doing today, and what's compute doing today to actually help the environment? So the first one is the mapping of the rainforest. This has been around for a long time. Before it was AI, it was data analytics. And what's happening here is companies, farmers, not farmers, ranchers in the Amazon get paid money for providing meat and leather products that are being produced without cutting down the rainforest. But it was always quite difficult to understand what they were doing. And this was a perfect use case for AI. So basically, the model was trained on looking at satellite images of the rainforest and working out what had changed and whether the ranchers were actually cutting down trees or whether they were protecting the rainforest. And then this data was used to provide input as to whether the ranchers were going to get paid for, and it was more for their leather products that they were selling into the fashion industry than the meat, because most of the meat was being consumed in Brazil anyway. But it was a way of being able to keep a check on what was actually happening in the rainforest by using an AI model, because AI models love this kind of thing. Train it on some data sets, go and look at some images and tell us what's going on in a way that would be very difficult for humans to do. And when we were using data analytics, it was quite a lot of work, but this was something, a real user case that was absolutely perfect. Another one, to go look on the Met Office, and my picture of the grid where we were losing power from wind. Well, if the national grid knows that that's coming and they can understand when we're going to start losing wind power, then that gives an opportunity to look for some of the alternative sources that we need to generate that power. So the Met Office has developed, well, because originally Met Office had HPC computers, and I used to work on building the HPCs, these big, huge computers in data centers. Probably about 7 or 8 years ago, they moved it all to Microsoft Azure in the cloud, because one of the problems with HPC environments, they need to be sized for the absolutely biggest workload. That only happens once a year, and then you're kind of left with these computers and not quite sure what to do with them. So by putting it into Azure, you can flex it and grow as and when the workloads come along. But now another criteria of the Met Office is actually there to provide weather information to the whole world. So countries which are going to be affected by climate change, you don't necessarily have a complex weather management recording system, can use the predictive information the Met Office is able to provide to them to then understand if there's risk of extreme weather events, to do some modelling, and this is really another important thing, because it looks at long-term modelling of weather patterns to try and understand how that will affect energy development generation, but also how it's going to affect countries and regions in the world. And it's really useful for us trying to understand how we're going to power our zero carbon grid, where we're going to be dependent on, the UK definitely more dependent on wind than solar, and we need to understand how weather patterns are going to affect how we generate energy. And the last one I quite like, and there's all over the world, lots of these projects, these are these AI autonomous ships. And this is definitely not a large language model. This is a little language model, because it's a little ship and they send it off, and it's got a lot of monitoring equipment, and they're traversing around the world. And in USA, you've got these great little sailing boats, and they just send them out into the oceans, and they sail around the oceans, and they've got solar power to generate their electricity, and they're just picking up data points and data sources, and AI captain helps steer them around and collect the information that's needed. It's a much cheaper, easier way of collecting using artificial intelligence to monitor vast expanses of ocean where you wouldn't necessarily be able to actually find anything. So that's my presentation in summary. Are there any questions?